Okay, so we have logarithmic functions today. So last class we learned about exponential functions. Well, the logarithmic function happens to be the inverse function of the exponential function. And some other properties of the log. So the way we say this, let me go to the top. So given this equation, f of x equals, we say this as log base a of x, where the base of the log has to be greater than 0 and the base cannot be equal to 1. This defines the logarithmic function. Okay, the domain of the log is from 0 to infinity, and the range of the log is negative infinity to infinity. And again, the way to read this notation is y equals log base a of x. And y represents the exponent on base a that yields x. So if the log and the exponential function are inverses of each other, this means that we can interchange any log into an exponent, and we can change any exponent into a log, as we see here. Y equals log base a of x is true if and only if x is equal to a to the y. So the way you rearrange from log to exponential is you take the base and raise it to that outside number of y. That'll give us a to the y power. And then you set it equal to the value inside the log, which is x. So this is how you go from log to exponential. So we'll definitely get more practice on that. Okay. All right. Next, it's called the common logarithm. So if you have log base 10 of x, this is called the common log. And it's usually written as just the log of x. That is just like the button you'll find on your calculator, log x. Okay, and if you see no log there, just understand that the base is 10. So if we wanted to convert the common log to an exponential function, we would write the base in there, log base 10 of x, and then we would convert from log to exponential. So you would do 10, raise it to the y, which is right here, 10 raised to the y, and then you would set it equal to x, which is right there. Okay, so we can go from log to exponential. And of course, we can go from exponential to logarithm as well, which we'll show in a moment. Okay, so that is the common log. So if you ever see a log with no base written, understand that the base is 10. Okay, next is the natural logarithm. And it's usually written as the ln of x. So if you see the natural log of x, this is the natural logarithm. And understand that the base of this log is e. So if you ever see the natural log, that base is always e. So if we wanted to convert the natural log to exponential, we would write that base of e, and then we would convert. We would say e raised to the y and set it equal to the inside of x, which is everything right there. E raised to the y equal to x. Okay. And the reason we have logs is because they take extremely large numbers and put them into a simpler format. So if you thought about it, I guess that explanation is down here. Well, when we get to it in a second, but so think about earthquakes. Whenever earthquake strikes California, they're like, oh, that was just a 7 or an 8 on the Richter scale. And you're like, okay, that's a 7 or 8. That must be bad. But the real math behind it, if you're going to shake a whole state, if you're going to shake a whole city, 7 just doesn't do it for us. If you're shaking a whole city, this means the earthquake shakes at about over maybe, I think about a million. I think they register them in millimeters. So you're looking like a million millimeters. And we just put it down into a simple format of 8. Like, oh, that was just an 8 on the Richter scale. No big deal. So this is why logs are created, to help us understand numbers better and not deal with such large values. Okay. So example 1, let's go ahead and rewrite all of these logs as exponential equations. So we're just going to do the conversions here. Okay. So for A, log base 4 of 16 equal to 2. To convert, we'll take the base and raise it to that outside number. So you'll get 4 squared equal to, and then you'll set it equal to the number inside the log. And you'll get 4 squared equals 16. So we just converted from log to exponential. And we actually got a true statement. 4 squared is 16. Okay, do it again. B, convert this from log to exponential. So you take the base of the log, raise it to that outside number, a to the c, and set it equal to the inside number of b. There it is. And then C says the natural log of t equal to d. So here we want to convert from natural log to exponential. So remember that the natural log has a base of e. So what we're going to do is take this base, raise it to that outside number. So e to the d is going to be equal to the inside number of t. All right, and that's going from log to exponential. All right, and now we're going to go from exponential to logarithm. So one thing to notice is that whenever you convert these, the base of the log becomes the base of the exponential function. Or you can say it the other way. If we're going to go from exponential to log, then the base of the exponential function will become the base of the log. All right. So I'll show you how to work this. Okay, so if we go from exponential to log now, we're going to take this base. So since 2 is the exponential base, we're going to put that as the base of the log. So this is going to go log base 2, and then it's going to be of the outside number, 1/8, set equal to the exponent of -3. There you go. So that goes from exponential to log. All right. And you can always check your work by just going back from log to exponential. We can say 2 raised to the -3 equal to 1/8. And we get the same answer as above. Oh, no, I don't want those. Ah, there we go. Okay. All right, B, do it again. All right, we have f to the h equals w. So we're going to do it again. This will be the base of my log. So we're going to get log base f of the outside number of w set equal to the exponent of h. That's it. Okay. And then we have e cubed is approximately 20.086. So since this has a base of e, we must use the natural log. So we're going to go base e. So we're going to rewrite this as the natural log base e of the outside number 20.086 equal to the exponent of 3. Okay, but since this is the natural log, we don't have to write that base in there as our final answer. Our final answer will just be the natural log of 20.086 equal to 3. There we go. So that goes from exponential to logarithm. So if you have a natural log or if you have a base of e, just know when you convert, you always must use natural log. But if it's anything else, such as the other two examples, you always use the regular log. Okay, so that's going from log to exponential and exponential to log. All right, any questions so far? Ooh, calculator time. Okay. So next up, we'll use the calculator. Let me hide this. And then bring up Desmos. Perfect. All right. And example 3 just says use a calculator to evaluate the expressions. There we go. And round to 4 decimal places. All right. So first up is the log of 643. So here I'll go to functions. Probably, is it under miscellaneous? It is. Log of 643. Close parentheses. And we get 2.8082. Okay. And then we'll do the natural log of 8946. So functions, miscellaneous, natural log 8946. And we get 9.0989. But if we're rounding, it's going to be 0.990. And then last is the log of 5/8. I'll go function log 5 divide 8. And we get negative 0.2041. Okay, so that is calculating logs. Easy enough, we punch them in the calculator. Okay, so just like I was saying about the whole earthquake things, logs, so this whole paragraph is explaining what I just said earlier. It says that logs will put any extremely large number into a simpler format. So that last paragraph says typical applications include magnitude and intensity of an earthquake, sound in decibels, pH levels. Oh yeah, that's a good one. Because if you think about a lemon or a lime, we just say, oh, the acidity level is like a 7 or 8. But again, there's a lot of math involved in that. Planet distances, even temperature. And of course, we'll use them for business applications too. If you're a millionaire, well, we can find out how to take your amount of money and put it into a smaller format for everybody else to understand. Okay, so they are involved in applications. So all this next chart wants us to do is plug all these numbers into the common log function. And we're going to see why it puts them into a simpler format. So why and how. So here, I'll just do the log of x. And I'll do my lovely little table. And let's type these numbers in. 1, 10, 100, oops, 1,000, and I'll do 10,000. You should start to see a pattern. So here at 1, we get 0. Uh-oh. Do reboot right now. I hope it doesn't. All right. 1, 2, 3, 4, 5, 6, 7. All right. So the log, again, takes these larger numbers and puts them into a simpler format. So we could even say that if you had $10 million, this means that you have 7 zeros, right? So all those zeros, 1, 2, 3, 4, 5, 6, 7. All right. Or if the magnitude of the earthquake was 10 million millimeters, there you go. It'd be a 7 on the Richter scale. Okay. Pretty sure I'm way off with those millimeter values, but again, just showing you an example. All right. So those are logs. Any questions on this first page? Oh, now, one moment. Record. All right. Okay. So here we have some logarithmic properties. So we learned some exponential properties on the last 2 lectures. It says since a raised to 0, so anything raised to the 0 is 1 in exponential form, then the log states that the log base a of 1 is always going to be 0, no matter what the base is. And since a raised to the first power is a, then the logarithmic form, log base a of a, is 1. Okay, so here is a table of basic log properties. Yes, it looks crazy, another type of language, but we'll go through these I'll go through these properties in the table as we work the examples below, so hopefully they make more sense. Okay, so the first column, log base a of a. So if the base is the same as the number you're taking the log of, then the result will always be 1. So we can compare that to the example below. Here, it says log base 12 of 12. Since these 2 numbers are exactly the same, then the log value will be 1. That's it. That's how it works. And that's why everything else in that column is 1, because if you have the common log, remember that the base is 10, and log base 10 of 10 is 1. And then for the natural log, the base of the natural log is e. So you have natural log base e of e. Since those numbers are exactly the same, you get 1. Okay. All right. And then the second column, I don't think we have an example for, but I'll write one. It says log base a, whatever the base is of 1, will always be 0. So if I said log base, let's just say log base 15 of 1, no matter what the base is, if you take the log of 1, it will always be 0. And that goes for the common log. Again, remember that base is 10. So log base 10 of 1 will be 0, and natural log base z of 1 will be 0. Okay, so that's the second column. Third column, we say log base a of a raised to the x will be x. So this is a consequence of the first column. So log base a of a raised to the x, well, we know that these will cancel because the base is the same as the number you're taking the log of, which means that all you will be left with is x. That's it. Okay. And then log base 10 of 10 to the x will equal x. So if I put log base 10 of 10, these will cancel and just leave you with x. And the same goes for the natural log. Natural log base z of v raised to the x will also equal x. Okay, and now we actually have an example with b below. This says natural log of e to the 5x plus 7. So since the base of the natural log is e, this part of the log will cancel and will leave us with the exponent of 5x plus 7. That's it. Okay. And then the final column. So first says a raised to the log base a of x will leave you with x. So if the base of this exponential function and the base of this log are the same, then they will cancel and leave you with x. And if you look at the common log, 10 raised to the log base 10 of x, since these bases are the same, they cancel and leave you with x. And same goes for the natural log. Okay, and we have an example below. This says e raised to the natural log of x squared plus 4. So we know that the base of the natural log is e, meaning the base of e and the natural log cancel, leaving us with the exponent of x squared plus 4. Okay, so that is just following these properties of logs. So if you have the same base on a log, either common log or natural log, they will always cancel and either leave you with 1 or 0 or the exponent. So that's what these logs do. Okay. All right. So next is more properties. It's called the change of base formula. So we use this formula to compute logarithms if your calculator does not allow you to type in any other base other than 10 or e. So the way the change of base formula works, it says if you are given log base b of x, we can ignore this one, then the way to calculate log base b of x is to rewrite it as log of x over the log of b. And an equivalent statement would be the natural log of x over the natural log of b. So if you need to compute a log and your calculator does not allow you to type bases in, then the way you can compute it is rewriting it as log x over log b or natural log x over natural log b. Okay. Which we will practice below. So let me get back to Desmos. Oh yeah, I need to open it again. Which Firefox? Doesn't matter. Okay, so let's go ahead and use change of base to evaluate these. Did it say round to anything? No. Okay, well, we'll round to 3 or 4 decimal places. Okay, so for the first one, by change of base, we can rewrite this as the log of 625 over the log of 5. And that's how you will type it in your calculator. So we'll say the log of 625 divide the log of 5. And look how nice that is. That gives us 4. Okay. And then B, log base 3 of 12.5. Well, by the change of base, I can rewrite this as the log of 12.5 over the log of 3. Put that in Desmos. Log of 12.5 over the log of 3. And we get, and I'll do this to 3 decimal places, why not? 2.299. Also, by the change of base, it's also equivalent to write natural log of 12.5 over the natural log of 3, and you'll get the same exact answer. And I guess I could show that here. 12.5 over the natural log of 3. And we get the same exact answer.
Professor, I have 2 questions for you.
What's up?
One, what's the difference between log and natural log? I came in a little late.
The bases. So a log is a log can have any numerical base, and the
Okay.
natural log can only have the base of e, which we learned last time.
Oh, all right, easy enough.
There you go.
And do you know if on the TI-83, if you can enter a base?
On the 83, probably not. I know on the 84 you can.
Cool.
So for you, you're gonna have to do everything like I'm writing it. Well, for you, you can type it in just like I wrote it.
Okay.
So if you type that in, I guess I could say, if you did log 625 divide log 5, then you'll get the same answer. So that's how you'll have to type it in.
10-4. Thank you.
Mm-hmm. Okay. And then last one, log base 2 of 11 over 16. Use change of base. You get log of 11 over 16 and log of 2. There we go. And we would get negative 0.541. Okay. So you may have caught it, you may have not. But if you look at Desmos, and if you happen to have a TI-84 or above, you can actually type in log bases here. So if I did log base A of A, look at this. I can type in 5 and then 625 and boom. Very nice. If you have the TI-84, I mean, you can check yours out, Charles, but there's a math button on your calculator. And if you hit the math button and scroll down, I think you'll see an option that says log base, but the 83 may not have it.
Yeah, I have that math button, but I don't see a log
Yeah.
base.
Yeah, if you scroll down, you'll see log base. But if you don't have it, then yeah, I don't think 83s have
No, an 84 laying around here somewhere.
it. All mine are at school. One day I'll get them back. Okay, cool. So that is using the change of base. All right. Next, we're going to solve the next three equations by rearranging from exponential to logarithm. So we did that on the first page. So let's go. And we're doing this to 4 decimal places. Okay. So this is 10 to the x equals 153. So remember to convert from exponential to log. The base of the exponential function becomes the base of the log. So this becomes log base 10, and then the outside number comes inside the parentheses. And then you set it equal to the exponent. So that is how we, again, convert from exponential to log. And now, since this is the common log, and to be the common log, it has a base of 10, we don't need to write that base in there anymore. We can just rewrite it as the log of 153. And now, just solve for x. Of course, by plugging it in your calculator. We'll say log 153, and we'll get 2.8. We said 4 decimal places. 2.1847. So what this answer says is that if you take 10 and raise it to the 2.1847, you will get 153. You can try it out, or you'll get close to 153. So 2.1847. There you go, 153. All right, let's do it again. B, e to the x equal to 0.3059. So since this has a base of e, we must convert it to the natural log. And the process is exactly the same. The base of the exponential function becomes the base of the logarithm. So we'll have natural log base e, and put the outside number inside the parentheses and set it equal to the exponent of x. And just like the last one, we had the common log. This is the natural log, and we know that the base of the natural log is e. So we can just rewrite this as the natural log of 0.3059. And all we have to do is calculate. So natural log 0.3059 and done. You get negative 1.1845.
So how would you even do that by hand? A very, very long equation?
Yeah, so back in the what was it, like I would say like 40s, 50s, maybe even 60s, there are books made for calculating logs and exponentials.
Jeez.
They're I might even have one in my shelf somewhere, but yeah, they're log tables, so you would just flip through the book until you found your decimal number.
Oh, dang. Well,
Yeah.
I guess that's easier than doing a bunch of math, though. Still.
Oh yeah. I did do a project in one of my classes before where we actually did do these by hand without using the book. Oh man.
No thanks.
It was a good time. All right. Yeah, that book's, I think I have that book. I don't know. I'd have to find it later. All right. All right. C, we're going to do the same exact thing. Convert from exponential to log. And now since this has a base of 1.02, we're going to use the regular logarithm. So this 1.02, that is our base. So this is going to become log base 1.02 of the outside number of 2 set equal to the exponent of 4t. Okay. And now we want to solve for t. So we're going to have to first calculate this log, which means we can use change of base on it. So I can rewrite this as log 2 over log 1.02 equal to 4t. So let's go ahead and calculate the left side, and then we'll divide by 4. So I'll do that in Desmos over here. Log of 2 over log of 1.02. Or I can even use that Desmos feature where I can type it in as I see it. It has log base A, punch that button, and I can type in the exact log I had. Log base 1.02, move over, type in 2, and a lot faster, of course. And here, to 4 decimal places, 35.0028 equal to 4t, and then just divide by 4. So I'll take that. Can I copy that? No, I'll just use our number. 35.0028 divide 4. And we get 8.7507 equal to t. There we go. That finishes that page, yes. Okay. Any questions on that page?
No, sir.
Calculator to save the day.
Yeah, these look hard, but they're not.
Logs are fun, man.
You enjoy math too much, I think.
I do. But logs literally make everybody's life easier. So especially when I teach calculus, you can use logs to make an extremely difficult problem. You can make it extremely easy, but students don't like to use logs, so they rather go the hard way and spend 30 minutes to an hour in a problem when the logs can help you solve the problem in like 2 minutes.
Yeah, I'll take the logs. I mean, hopefully I don't have to take calculus, but
no.
If I do.
Well, if you do, you'll take business calculus, which is the easy calculus.
Okay, good to know.
There you go. All right. Do I need to calculate anymore? Not yet. Okay. All right. So we have more log properties. Ooh, and these are the main properties for logarithms. The other ones that we learned above, you can simply type them in a calculator and get these answers. But these properties are the ones that make life easy. So number 1 is called the product rule. So this says that if you have the log base A of products m times n inside your log, then you can expand the logs into addition. So this says that log base A of mn can be rewritten as log base A of m plus log base A of n. So to write an example of that, where am I? There we go. Let me zoom in. And for my example, if I said log base 2 of x times y, I can rewrite this as log base 2 of x plus log base 2 of y. But of course, it can be more than two terms inside the parentheses. Let's say I had log base 3 of x, y, z. Then this would be log base 3 of x plus log base 3 of y plus log base 3 of z. And of course, it works for numbers as well. Maybe I can do another one. What if I said log base, or what if I just said the regular log? Log of 5x, why not? That would expand to log 5 plus log x. So all we're doing is taking these products and expanding them into the sum of logarithms. And the crazy thing about this is you can reverse these. So let's say you started off with log 5 plus log x. You can put it back as the log of 5 times x. So you can reverse engineer these properties. Okay, so that's product to sum. Next is quotient to difference. So if you have a quotient inside the log, then you can expand it by subtraction. So the log of m over n is equal to the log of m minus the log of n. So that would be, I can use the same examples above. I can say log base 2 of x over y is log base 2 of x minus log base 2 of y. And then I can say log base 3 of, let's say I had, oh, well, would have to make it a little more difficult. So I don't want to make it too crazy. Let's just say x, y over z. Then this would become log base 3 of xy minus log base 3 of z. And then if you wanted to, you can take this and expand it by the product to sum. So you can keep expanding, but I only wanted to show quotient to difference. But just know that we could keep expanding that one. All right, I don't think we need another one. Okay. Third one is the power rule. All right, the easiest one. The power rule says if you have the log base a of m to the p power, then all you have to do is take that power and move it to the front. That's it. It becomes p times the log of m. Nothing crazy. So good example of that. Let's say I just had log base 5 of x to the 10th. Well, by the power rule, that 10 would come down and you'd get 10 log base 5 of x. That's it. That power comes down. Let's say I had natural log of x to the 5th. Then you'd add 5 natural log x. That's it. Oh yeah, and all these properties also work for the natural log. I guess I should have thrown that in there. Here, I can just change these up. I'll make this the natural log of 5x, which gives me the natural log of 5 plus the natural log of x. There you go. And then I can make one down here. Natural log of x over y. Oh, sorry, not that one. Let's say 5 over x. You'd have natural log 5 minus natural log x. There we go. Okay. And then the last property is called the equality property. So remember that exponential functions and logs are inverses of each other. So last class, we learned about the exponential equality property, where it said a to the u equaled a to the v. If the bases are the same, then u equals v. Well, the same goes here for logs. If log base a of m equals log base a of n, if the bases are the same, then m will equal n. Okay. So we have a log equality property. And good example of that, let's just say I had log base 2 of x equal to log base 2 of 4. Since these bases are the same, then x would equal 4. There you go. Or let's say it was natural log y equal to natural log 10. Well, we know that the base of the natural log is e, so the bases would be the same, and y would equal 10. So that is the equality property for logs. So many properties. Not really, it's just 4. Okay. Any questions on that?
No, those were easy too.
All right. All right, 7. I think that's it. Ooh la la. So 7 says solve each equation. So we're going to take everything we learned today and solve for x. Okay, so A, log base 3 of x plus 4 equals 2. Our job is to solve for x. So the only way to solve for x is to convert this equation into an exponential equation. So if you ever get stuck on a log, just know that you can always convert a log to exponential. So if we convert log to exponential, I'm going to get log base 3 and raise it to that outside number of 2. So this is going to become 3 squared, and you set it equal to the number or terms inside the log. So you're going to get 3 squared equals x plus 4. And now all we have to do is solve for x. 3 squared is 9. You subtract 4. X is equal to 5. There we go. All right, all good on that one?
Yes, sir.
Okay. All right. B, the natural log of e to the x squared minus 3x. Okay, so this one is going to use the property we learned on the second page. So this says natural log e, base e, of e to some exponent. So remember that if the base of your log is the same as the number you're taking the log of, then they will cancel and leave you with that exponent, whatever it is. So this means for this problem, the natural log of e raised to the x squared minus 3x, this part will cancel and leave us with the exponent of just x squared minus 3x equal to 10. So that was by one of the properties on the other page.
So if you're canceling the base and the number, it gets rid of the natural log or the log.
Exactly. So if this said instead log, let's say it was log base 5 of 5 to the x squared minus 3x. Since this number and that number are the same, you would still be left with the exponent.
Cool.
Okay, and now we just solve for x. And what we have is a quadratic equation, which means you're going to move that 10 over and hopefully factor this equation. This is minus minus, so this means you'll have x plus a number, x minus a number. And what are the only factors of 10 that could give me -3?
2 and 5.
2 and 5. And since 3 is negative, the bigger number 5 will be negative, and 2 will be positive. And our answers here are x equals -2 and x equals 5. There we go. All right. Cool. All right. C. Log base 10 of x squared plus 5x plus 16 equal to 1. All right. So this is just like A above. So here we are stuck in log form. So we're going to convert from log to exponential. So this means we're going to take this base of 10, raise it to that outside number of 1. So 10 to the first power, and then you set it equal to everything inside the log. X squared plus 5x plus 16. Okay. We got rid of the log, and now again, we have an exponential equation. Well, 10 to the first power is just 10. So all we're going to do here is subtract the 10 to the right side, and you'll end up with 0 equals x squared plus 5x plus 6. And once again, all we have to do is factor it. That's plus plus, that's easy. What are the only factors of 6 that give me 5?
1 and 6.
That would give me 7.
Oh, negative.
No
1 and 6.
negatives.
Oh shoot!
What
Right, yeah. 3 and 2.
There you go. 3 and 2. And our answers here would be x equals -3 and x equals -2. All right. All good?
Yeah. Perfect.
Okay. All right. And then D. Log base B of x plus 2 plus log base B of x is equal to log base B of 24. All right. So what we want to do on this one is combine our logs. So these two logs can be reverse engineered by using that product to sum formula above. So remember that this, if I had, let's say I had log base A of x plus log base A of y, then we can put this back together as log base A of x times y. So that's what we're going to do here, since these have the same base of b. So log base b of x plus 2 and log base b of x, this will become log base b of x plus 2 times x. equal to log base b of 24. Okay, so we took those two logs, the sum of those two logs, and we put it back as a product. Okay, now we can use another property. So these logs have the same base. So now we get to use the log equality property. So if this said log base a of x equal to log base a of y, then since these are the same base, x would equal y. So that's what we're going to do here. So log base b of x plus 2 times x equal to log base b of 24. Since they have the same log base, we're going to take x plus 2 times x and set it equal to 24. Okay. And now we just have to solve for x. So what we're going to do is distribute the x on the left side. That should give us x squared plus 2x equal to 24. Then move the 24 over to the left and factor it. I hope we can factor it. That's plus minus, which means you would have plus, you'd have minus. And what are some factors of 24 that can give me 2?
6 and 4.
6 and 4. Good. Since 2 was positive, the bigger number must be positive. And now if you solve for x, we get x equals -6 and x equals 4. All right, cool. And those are logarithms. And all the
Easy enough.
properties, good. All the properties associated with them. Okay, and we are done.